Hello everyone, welcome back. In this video, we're going to talk about a technique for evaluating indefinite integrals, which is called the substitution rule. Now, the main goal of substitution is to simplify the integrand so that it is easier to find its antiderivative. So let's consider the example where we have the integral of cos 2x times 2 dx. Now, the table of indefinite integrals does not tell us how to evaluate this integral, or more generally, integrals which take on the form f of g of x times g prime of x. However, if we introduce a new variable, we'll call it u, and define it to be the argument of cos, which is 2x, then its derivative, du over dx, is equal to 2. And if we solve for du in this equation, we get that du is equal to 2 times dx. So here we're treating du over dx like a fraction, and so we can multiply both sides by dx. Now notice that we can substitute these expressions into our integral. So 2x is equal to u, and 2 times dx is equal to du. And so now our integral will be simplified in terms of the new variable u. So our integral is cos of u du. Now we can look in our table of indefinite integrals to find the general antiderivative of the cos of u, which is the sine of u plus c. And in the final step, we can substitute back the original variable. Our original variable was in terms of x, and we know that u is equal to 2x. So now the antiderivative becomes the sine of 2x plus c. So this method is called the substitution rule, and it works backwards to undo the chain rule. And we can always check whether or not we have the correct antiderivative by differentiation. If we take the derivative of the sine of 2x, we should get the cos of 2x times 2. So let's have a look at some examples of using u substitution to evaluating indefinite integrals. So in the first example, we have the integral of 2x times the root of 1 plus x squared dx. And one of the key things to look for when you want to choose a substitution is to pick a function such that its derivative is also in the integrand. Now, this won't always be the case, but it is a good starting point. So if we look at the function 2x times the root of 1 plus x squared, we can simplify the integral by choosing u to be 1 plus x squared. So if u is 1 plus x squared, then the derivative with respect to x is going to be 2x. And notice that the derivative is also in the integrand. What we see is a 2x in front of the square root. Now, if we were to solve for du in this equation by multiplying both sides by dx, we end up with 2x times dx. So notice that the dx and the 2x can be replaced with du. And so now the integral of 2x times the root of 1 plus x squared dx is equal to the integral of the square root of u times du. So now let's rewrite the square root as an exponent. So now this is u to the 1/2 du. And so now we're treating u as our variable, and we can find its antiderivative. So the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2 plus a constant. So we can simplify our coefficients. This is 2/3 u to the 3/2 plus c. And in our last step, we're going to substitute back the original variable. So we know that u was 1 plus x squared. And so the antiderivative is 2/3 times 1 plus x squared to the 3/2 plus c. So now let's have a look at the third example. We have the integral of the tan of x. So we know that the tan of x is equal to the sine of x over cosine of x. And so we want to find the antiderivative of sine x divided by cosine of x. So here we're going to look at making a substitution. And so there are two different functions we could choose for u. So we can choose either u to be sine of x or u to be the cosine of x. Now for this particular integral, only one of these substitutions will work. So if we let u be the sine of x, then du over dx is equal to the cosine of x. And if we solve for du in this equation, we get cosine of x times dx. But if we notice in our integrand, we don't have of cos of x times the dx. What we have is 1 over cos of x times dx. So for this particular substitution, this will not work. So now let's try to look at making the substitution where u is cos. If u is cos, then du over dx is negative sine of x. Now notice that we have a sine of x dx in our integrand. So if we solve for that from this equation, we get that du is equal to negative sine of x dx. And so negative du is equal to the sine of x dx. So we can substitute the denominator with u, and the numerator is equal to negative du. And so we get the integral of sine of x over cosine of x dx to be the integral of 1 over u times negative du. Now any constants can be moved outside of the integral. So we can move the negative outside. And we have the antiderivative of u to the negative 1 du. And if we look in our table of antiderivatives, the antiderivative of u to the negative 1 is equal to the natural log of the absolute value of u plus a constant. And in the last step, we replace u back with the original variable. So this is negative natural log of cos x plus a constant. Now let's have a look at number 5. We have the integral of dx divided by 3 minus 5x. So here we're going to make a substitution. We'll let u be equal to the denominator. So u is 3 minus 5x. The derivative, du over dx, is equal to negative 5. So here, if we solve for dx in the equation, we get du is equal to negative 5 dx. So negative du over 5 is equal to dx. So now if we substitute this into our integral, we get the integral of 1 over u times negative du over 5. We can move the negative 1 over 5 outside of the brackets, or outside of the integral. So we get negative 1 over 5 times the integral of u to the negative 1 du. And if we use our table of antiderivatives, we know that the antiderivative of u to the 1/2 is the natural log absolute value of u. And so the antiderivative is negative 1/2, or negative 1/5, natural log of absolute value of u plus c. And lastly, if we substitute back u, which is 3 minus 5x, then this is the antiderivative. So now let's have a look at number 7. We have the integral of e to the cosine of x times the sine of x dx. So here we want to choose u such that its derivative is also in the integral. So here we're going to choose u to be the cosine of x. Then its derivative, du over dx, is equal to negative sine of x dx. And we notice that there is a sine of x dx in our integrand. Oops. And that shouldn't be a dx here just yet. So if we multiply both sides by dx and divide by negative 1, we get negative du is the sine of x dx. So now we can substitute this into our integral. We get the integral of e to the u times negative du. We can move the negative outside of the integral. So this becomes the integral of e to the u du. And the antiderivative of e to the u is e to the u plus a constant. And in the last step, we substitute back the original variable. So we have negative e to the cos of x plus c. So now let's jump to number 9. We have the integral of x squared over x cubed plus 1 dx. So here we can choose the substitution. U is equal to x cubed plus 1. We see that the derivative, du over dx, is equal to 3x squared. And we see it x squared dx in the numerator. So if we multiply both sides by dx and divide by 2, or divide by 3, we end up with x squared dx is equal to du over 3. So now if we make the substitution, we get 1 over u times du over 3. So this becomes 1/3 the integral of u to the negative 1 du. And the antiderivative is the natural log of the absolute value of u plus a constant. And substituting back the original variable, we get 1/3 absolute value of, or the natural log of the absolute value, x cubed plus 1 plus c. Now let's have a look at number 11. We have the integral of x to the 6 times x plus 1 squared dx. So for this example, we actually don't need to use a substitution. So if you were to expand the x plus 1 squared term, we get x squared plus 2x plus 1 dx. And then distributing the x to the 6 through the brackets, we get x to the 8 plus 2x to the 7 plus x to the 6 dx. And then we can find its antiderivative to be x to the 9 over 9 plus 2x to the 8 over 8 plus x to the 7 over 7 plus c. And we can simplify the coefficients. So that's x to the 9 over 9 plus x to the 8 over 4 plus x to the 7 over 7.